Okie dokie. Yeah, so I'm recording. We can just go ahead.
Okay, thanks for the invitation here to discuss some paper that started when Soren came in 2018. We were discussing in the office, and for different reasons, it took a bit of time to conclude. But finally, it's out, and so the idea is to continue these ideas that different authors have worked on how to calculate perturbations on top of non-equilibrium backgrounds. And the reason for us is that in ultra-relativistic heavy-ion collisions, that's precisely what happens at early times. So we are trying to understand what happens at early stages. And one of the first questions is like, can we calculate a very natural object that carries information against perturbations, which are green function? And then beyond than that, we also wanted to understand, like, okay, there are different ways or different models that you have to describe this non-equilibrium region in the space-time evolution. And if you put more detail, microscopic details, you expect to have better results or to have more physics. But in practice, does this matter how much microscopic information you have at the level of perturbations of the energy momentum tensor? And this was precisely some of the questions that we tried to address in this work. And in order to do that, we use those new concepts that have been developed also for years and partly by us in NC State, which are related with attractors in hydrodynamics. And so, for people who are not familiarized with those attractors, sorry, somebody was calling me. People who are not familiarized with attractors, it's just basically phase space regions in space regions in the phase space of variables, where you see accumulation of points after some time, and regardless of the initial condition that you have, all the solutions of any type of equations merge there. And this is
the voice here is ununderstandable.
Do you hear me? Do you hear me?
Now, yes, but for the last 40 seconds, nothing was understandable.
Okay, so I will speak for my cell phone then, because I think that is the computer issue. But I will have an echo. Let me try to figure it out something here.
That's also quite bad.
Mm-hmm. Better?
Yeah, so now we have a lot of echo. So it may indeed be, so if your sound comes, I see you twice. So your sound now comes from the cell phone?
Okay, I will just use the cell phone, which is better, and then I will disconnect from my computer. So well, then I will appreciate it.
I think you just have to turn the sound off on the computer so that there's no echo.
Okay. Better?
Yes.
I think so.
Okay.
Yeah.
Okay, I did. I thank you for pointing me out. So I will talk by the cell phone, and then I will just continue moving the screen. Okay, so in order to start, let me just give the basics of the model that we are going to use, and it's in equation 1 in page 2 here. Do you see the mouse, by the way?
Mm-hmm.
Yep, I can see the mouse.
Okay.
Yeah.
Sorry, it's just that I don't know. So that is the Boltzmann equation in the relaxation time approximation, and I am assuming that the system is described in biweekly couplet systems, where the quasi-particle picture holds, and therefore the evolution equation is the Boltzmann equation. But in this case, we are going to model this function C of f is in general a very highly nonlinear expression, and I'm going to consider a deviation from the equilibrium. That's why I'm taking here the value of the function minus the equilibrium, and it's just taking into account how further away I'm from equilibrium. And there is a parameter that enters here, which is the relaxation time, which is, you can imagine that is the typical time between two collisions among two particles in the system. And the object that I'm going to focus on is the energy momentum tensor, which is in terms of kinetic theory is nothing else than an average over the space-time, over the momentum, phase space of momentum. Like for instance here, I am just doing an integral of certain observable, and is weighted probabilistically by some function, f. And that's the way that you reconstruct, in general, observables in kinetic theory by using the distribution function. So for instance, the energy density, when you are in equilibrium, as we know in a relativistic system, is proportional to T to the 4. This mu f is some, takes into account the degrees of freedom, and this p squared over 30 appears for the statistics that you have. In this case, we are going to assume a Bose-Einstein distribution function, since we are interested to compare with a more generic collisional kernel for QCD based on the hard-thermal loop theory. Okay, so on the other hand, I am going to consider first that there are two parts. One is the background, and the other part is the fluctuation. Let me just focus in the first part of this talk about the properties of the background. And the background is a system that is expanding only longitudinally and along the C direction. So imagine that you have a three-dimensional cylinder, and it's expanding in just in one direction, and the other ones are frozen. And in that case, it's convenient to change the variables in the Milne coordinates, defined like in this proper time, doing a proper time tau, and this var sigma, which is the rapidity. And in that particular case, the total full Boltzmann equation takes this form. Now, after some major rearrangements, you can really show that equation 15 is the equation that you want to solve in practice. So notice that this is taking into account all the evolution. So as I say, we are going to split the distribution into pieces. One, which is the background, which describes the evolution of this cylinder. And the other one is the perturbations. We describe perturbation around this particular cylinder. So let me just focus about the physics and the main features that we already knew from years about this background. In this particular case, we are going to consider, in this cylinder that I was talking about more precisely, is Bjorken flow model, yes, which consists into a system that just expands longitudinally, but at the same time, there are some other constraints related with the invariance in the reflections around the C direction. And the other one is that the system is invariant around boosts around the C direction. And in that case, the symmetries, those type of symmetries, which can be encoded in a group form more formally, but let's avoid that discussion, just tells me that the distribution function is invariant, is a function, this 7-dimensional dependence of this distribution function gets reduced to only 3 variables. One, that is this proper time tau. Second, the transverse momentum, because I don't have any dynamics in the transverse plane to the longitudinal direction. And this p bar sigma, which takes into account the longitudinal momenta around this direction, and this is invariant under boost. So it captures all that particular physics. And when you make an average over the momenta, for instance, when you want to calculate the energy momentum tensor, you just have four terms: the energy density, the transverse pressure in the y direction too, and the longitudinal pressure, which is rated in for the Bjorken case like this, where tau again is the relaxation, is the proper time. And the energy density is nothing else than those averages, as I said, over the background. So keep in mind that those are averages over the background. Now, the trace, we are considered a conformal system, and the traceless condition translates into this expression that the energy is 2 times the pressure plus the longitudinal one. And also, because of the symmetry, the fluid velocity of the system, this U nu that I didn't define before, is nothing else than the fluid velocity in the local rest frame, because the 3 spatial components are all of them 0. So it's a time-like vector in this case. And for the background, the distribution function takes this particular and very simple expression. So you see that there are no spatial gradients because the symmetry kills them. Basically, there is no dependent on them. And also the deviation from the equilibrium between the background and the equilibrium distribution function. Okay, so what is the strategy? So this equation, although it looks very simple, is extremely highly non-trivial. Why? Because in general, the relaxation scale here is a function of the energy, or in other words, the temperature of the system. So every time that you want to solve the equation, you need to know the information of the temperature, and the temperature depends on the distribution function, and the distribution function depends on the temperature. We have developed with years techniques to do that, and it's a simple one-dimensional Volterra type equation, integral equation. I'm not going to go into those details, but it's possible to solve it numerically. However, there is another way to do that, which is okay. I can. What happened here in my computer? Okay, but the computer frozen as I was expecting. Let me just see something. I think I will be better if I continue in the cell phone, and then I will explain what the equation goes. Is it fine for everybody? Hello? Hello?
Yes, that's fine, Mauricio.
Okay, because something is happening here, and otherwise it would be. So I will just be indicating the figure and the equation.
Okay, that's fine.
So
Yeah, sorry about this.
let me see. I can share the document on my computer.
Okay, that would be great.
Oh, okay. I could also do that actually. Yeah. Okay. Go ahead, Thomas.
Okay, give me just 1 second.
Mm-hmm.
So
Yeah.
so that was the equation, and here's
Yes,
the moments.
so that's what I was trying to say. That so this is you can solve again equation 20 numerically, but there is another way which actually tend to be much more efficient in certain aspects. For instance, when you do really more complex system, which is using moments of the distribution function. And moments of the distribution function are certain. The way that I like to understand them is like the following: like the distribution function has different values as a function of the momenta, also the space, but let's assume that I am not focusing on that. So what I do is then to weight every possibility that that the function takes by evaluating its value after averaging over some function that can depend on the energy, or in this case, as I defined it in equation 21st, of the angles, the phi pi and theta p, where theta p is the azimuthal angle that is defined by the ratio between the longitudinal momentum and the energy, and the tangent of phi pi is basically the ratio between the x and y components of the momentum, which in this case they don't play a role, but we define it like that for because it's important for what comes at the level of the perturbations. So, so that those moments have an advantage when you do that like that, which is the following. Like if you go to the next page, equation 27, is an equation that captures. So you just use the definition and you use the Boltzmann equation and you do a little bit of derivatives. And then you find that those equations those moments have a differential equation that describes its evolution. And it's a tower of equations because, as you see, it depends, the value of the evolution of the moment L in equation 27 in the left-hand side depends, according with the right-hand side, with the moment that is of order L minus 2, the same one L, and L plus 2. So you pay a price by using this. First of all, is that you have to do truncations systematically because, as you see, depends on the order L plus 2. So if you want the order L, the solution for L, it would depend on the L plus 2, and so on and so on. So analytically, it's not really easy to solve it, but you can do it in a computer in a very simple manner. You just solve this equation, you put certain condition, and you start to do systematic truncations. And at some point, you will see that numerically, the solution has converged towards a very, very particular value. And I will show a plot where we see this. So that is the advantage of using this method. And actually, the rate of convergence can be extremely fast. So in general, when you evaluate low moments in L, by L increasing from 0 to infinity, then you will see that you don't need to go to infinity to have a very good convergence. Just like by numerically, just by tuning, you will see like with 8 is more than enough, or 10 maybe, for at the level of the energy momentum tensor. So that is kind of cool way to understand this. And the other part that is also interesting about this equation is that this equation encodes, although it's not easy to see that when you write it like in this way, that it has some resurgent properties in the sense that you can really show that at late times, the solutions have the perturbations around the fixed points of those differential equations have some exponential terms that are non-perturbative and analogous to instantaneous. And that was precisely what we did with Shaw, Liresta, and Hao Cheng in reference 53 to 55. Now, so the next part that we start to do is let's start to use this type of tools to understand a little bit what are the universal properties of this equation and compare with the kernel that you have in perturbative QCD. And we use some particular initial condition that for phenomenological purpose has been used for a while based on color glass condensate picture that tells you like at very early times the distribution function is basically delta Dirac function in the longitudinal direction. It means that you don't have basically zero longitudinal pressure, and then you have just a distribution in the transverse plane as a function of the transverse momenta. And this type of distribution allows you to basically initiate your differential equation. So this is the kind of differential equation when you plug in the average that you do, the initial condition that we use. And it's just nothing else than a condition that we have to solve this numeric. And again, what we are going to do is to solve the differential equation 27 by systematically truncating. Say we go to L equal 10, and we truncate all the moments above, and we see how good the numerics is start to converge towards a unique value. Of course, it's a thing that is a trial and error, but it's very efficient. And there are two models that we consider in this case. One, which is what happens when the relaxation scale is constant, and what happens when it's a time-dependent function, which it can happen. So before we continue, let me just say some words about hydrodynamics. Because hydrodynamics is the theory that emerges at late times. So it is worth to just analyze what we expect at late times. And the conservation law for the energy density is given by this expression. So this is the evolution of the energy density, and it depends on the longitudinal pressure that carries information of the shear viscous tension via the equation 35. And it's nothing else than an equation that tells you how the energy cools down as the system expands longitudinally. So then if you use gradient expansion up to second order, the gradient expansion asymptotically gives you this expression, equation 36, when you have a term, the first term that is like proportional to eta, where eta is the shear viscosity. And it's 1 over tau because the system is expanding, and therefore the gradients are proportional to 1 over the time, because that's the expansion of the volume, basically. And the first gradient is, of course, is 1 over tau. The next one is 1 over tau squared. And those coefficients that appear here, this lambda1 and this tau pi and second order transport coefficients. And in the relaxation time approximation, there is something really nice that you can calculate them very easily. And you can find the references here, equation 37. And for that particular collisional kernel, the shear viscosity over entropy ratio is related with this relaxation time, the tau pi that you have, which is the relaxation time of your shear viscous tensor, is nothing else than the original relaxation time that you have that you choose in your collisional kernel. And this lambda1 that captures some nonlinearities when you do this gradient expansion until higher orders ended up being proportional to the product of this tau r squared times the temperature times S. So, okay, so let me just continue explaining a little bit the questions, and then I go to plots figure 1 and 2. So the other aspect that it is important to do is like, what is the expansion? Given this expansion of the shear viscous tensor, equation 36, how does it look at the level of the energy density? So you want to expand until second order the solution, the asymptotic solution of the energy density, and you ended up finding that it is possible. And the result is quoted in equation 38, and when we use equation 37. And basically, it's nothing else than the solution, the asymptotic solution of the differential equation that you have for the energy density by using, again, the gradient expansion of the shear viscous tensor. And in that particular case, there is a constant that appears there, which you can factor out completely, which is this tau to the 4/3 times the energy at infinity, which can be basically calculated from the Boltzmann equation itself. And what we just did is like, how does it look, this asymptotic expansion? And when we compare with the exact solution in the relaxation time approximation by calculating the energy density, the number is quoted here, and it's 1.2 tau r to the 1/3 times the tau to the times the energy at times and tau equal to tau 0. So this is a constant that appears there, and that determines that constant, so we can really have confidence over the result that we have by doing the gradient expansion asymptotically. The reason to do it asymptotically is that at late times you expect that the all the dissipative, the nonlinear dynamics that you have in the original Boltzmann equation goes away, and the only thing that matters are small deviations from equilibrium, and therefore that is kind of universal. That is the so-called attractor that everybody is talking about. So is this that particular aspects that do not change regardless of the initial condition, and this is precisely what we are trying to illustrate here.
But
now,
this 1.2, that is for a specific initial condition, isn't it? It's for this, it's for...
No, that is for the, that comes from the, that's why the initial condition is encoded in this tau times energy at time equal tau 0.
Mm-hmm.
But the important aspect is this tau r to the 1/3.
But I mean, the 1.2, that depends on this assumed form 29, doesn't it?
29? No, because that is precisely the initial, that determines the initial value. So this tau times energy at 0, which is kind of constant, is determined, yes, but 29. But that is like, the only...
If I replace the delta function by something else, then I would get some number other than 1.2, wouldn't I?
You will, indeed, but that is, in our case, we take it like constant.
Yeah, okay. So it does, so the 1.2 in some sense does depend on this kind of color glassy initial condition, does it?
Yes,
okay.
Yes, yes, yes. So, okay, so as I said, there is something interesting when you evaluate. There are two quantities that usually you think about when you are doing hydrodynamics, and one is some quantities that is the inverse Reynolds number and the Knudsen number. So to give an idea, the inverse Reynolds number is just a dissipative quantity that measures dissipation when you compare inhomogeneities at large distances, while the Knudsen number is more related with the ratio between the microscopic and the macroscopic scale, which in this case could be, for instance, the mean free path, being the mean free path, the microscopic scale, and the size of the system, which in this case is nothing else than the distance that is at which this cylinder is expanding from its origin at zeta equals 0 along the longitudinal direction. So the ratio between those two quantities can be quantified and is given in equation 40. So you see that is the ratio between the shear viscous tensor and the enthalpy, which is the energy plus the pressure, and the factor tau over tau r emerges because when you kind of replace what is the value of the Knudsen number. And the interesting aspect of that is that this quantity, this ratio, allows us to define up to some extent some relaxation time, because at late times we know how the shear scales with the relaxation time via the gradient expansion, and therefore it allows to just like test ideas about like how farther I am when I am in equilibrium. Can I define some sort of transport coefficient far from equilibrium? And these are some ideas that, by the way, we have also explored with Shou, Hao, Sheng, and Ali. And we show that indeed, when you do this resurgence structure of those equations, you can really define them. However, doing resurgence, and we learn it painfully, it's a very complicated in general. So one way to kind of learn automatically about whether or not you can define an effective relaxation scale is by comparing this ratio, which can be obtained directly from the numerical simulations and try to understand what's going on in the mirror. So that's also the purpose of this type of exercise. So, okay, so let me just now go to the figure 1 to start to explain what is happening. And at the top, I just plot the different components of the energy momentum pressure divided by this constant that we plot there, this E tau to the 4/3 and infinity. So that's way, in that way, we get rid of any initial condition dependence. And the reason is, again, as I say, is just to compare what are the universal properties. And here I show the three lines at from the top to the bottom are the 3 times the transverse pressure, the energy density, and 3 times the longitudinal pressure. So the first thing is that an alpha function of this x, which is nothing else than the value of tau over tau r. And this x is nothing else than a measurement of the inverse Reynolds number. The inverse Knudsen number. So when this x goes to infinity, then the Knudsen number is very small and the system goes to equilibrium. And this is what you see in at the top of the figure when the 3 blue lines are always merging, because the system is equilibrated and all the transverse and longitudinal pressure became the same. And they scale with the energy because of the conformality of the system. But as you see at very, very small x, when the Knudsen number is very large, there are large deviations, and you see that because the ratio between the longitudinal and the transverse pressure is way, way, way farther from 1. The other aspect that you see is the scaling of the energy density at early times with the free streaming solution that can be estimated, because free streaming is no interaction, so your relaxation time scale is basically infinity. And in that case, the Boltzmann equation allows you to get an approximative solution that scales with this variable x as x to the 1/3. And in that case, you see that there is a very, very good agreement, which just tells you, like, at very early times and regardless of the initial condition, you have basically free streaming, so no interactions is what dominate that particular regime. While at late times, the system is very well described by the gradient expansion, which is precisely this red dotted line that you have here. And what happens in the middle is precisely how the system hydrodynamizes, or what is the dynamics that leads you there. And the purpose of this plot was just to illustrate precisely that gradient expansion works, but it's only at late time. So hydrodynamics is not enough to describe this system. And the other part is that for weakly coupled systems, this free streaming dominates at early time, and that is what slows down the evolution when you compare with ADS systems. So ADS does not have this type of free streaming behavior, and the reason is they don't have quasi-particle picture. They just have a relaxation scale, which is very, very short, and therefore the system thermalizes very quickly, hydrodynamizes very quickly. Now, in the second part, in the second plot at the bottom of figure 1, you see this ratio of this effective relaxation time scale with given by equation 43. And what we did showing here is precisely what happens when you solve the exact Boltzmann equation. So you can do that. We have a solver that does this. And what happens when you start to kind of to match to increase the number of moments. As I say, that's the advantage of using those moments method, that we went from L equal 4, but you see these dotted lines, the blue line. And you start to also compare with what happens when you have L equal 8, when it's this dash dotted line. And you see that between the L equal 8 is already matching most of the curve. And it's just a test that the method that you use of moment converges very fast and very efficiently. So that is kind of cool. And you see also something else, and is that the Navier-Stokes hydrodynamical behavior, which scales with the relaxation time, because the cheater scales with the relaxation time, it starts to go towards, it's constant in this case, so it's going to 1. But then you see that all the blue lines start to merge slowly towards that value, which is a very good result, because it's telling us like we are again capturing the late time behavior that you see at the bottom, where the Navier-Stokes coincides with the energy density. So okay, so this was for a relaxation scale which is constant. What happens if you do the same exercise when you have something that is depending on the temperature, or in other cases, the scale of momenta of your particle. In this case, let's assume that the scale of momenta is on the order of the temperature, just to see what are the differences. And here we have a different comparison. We have at the top of the bottom is again the energy momentum tensor scale over this E tau to the 4/3 to infinity. And the reason is that when you change the relaxation scale, you also change the value of the evolution, and we rescale here as a function of a different value, which is a different variable, sorry, which is the temperatures times the time scaled by 4 pi over E over S. The reason of that variable is this is analogous to the other variable that we defined previously, but it's nothing else than the way that the relaxation scale is, since it depends on the temperature, it's inversionally proportional, so that's why it appears. And again, this W has an interpretation which is related with the Knudsen number for the system. And okay, so here we have different comparisons. The blue lines are the components of the energy momentum tensor when you have this time-dependent relaxation scale. And here we start to compare really with the leading order, the full leading order QCD kinetics that is obtained in this algorithm called compost, and the free streaming, which is a scale like that. And again, let's keep in mind that the free streaming slightly gets affected when you change the relaxation scale, so you have to tune this C infinity. And also the Navier-Stokes result. The first thing that you see is that although at the level of the energy density, so the figure in the middle, so again, free streaming is more or less what defines the early time behavior, no matter what theory you have. But you see very little difference between the black and the blue line for the energy density when you have either relaxation time approximation or QCD kinetics. So although, as I said at the very beginning of my talk, QCD kinetics contains all the microscopic physics, at least at the order of resummation. But this relaxation time, which is extremely simple, really, really simple, and it doesn't tell you much about diffusion of momenta and so on, it's really fair enough approximation compared with the full QCD kinetics. And the difference, at least in this plot, when we quantify it, is less than 10%, or 10% maximum in this interval where they disagree. The other important aspect is that when you really rescale in these variables and you write the information of the energy momentum as we did in the vertical axis, you see that asymptotically, no matter what microscopic theory you have, you are matching the gradient expansion again, which is a good indication because this system relaxes towards hydrodynamics at late times, regardless of the microscopic theory. So in other words, the attractor of those two theories in large times is nothing else than second order hydrodynamics. And this is a very nice way to see that. Now, if you compare now something analogous to the relaxation scale, but in this case with eta over s, by defining eta over s, some effective transport coefficient far from equilibrium and the value asymptotically, which is what you have here in this plot at the bottom. And you compare, okay, let's assume and let's use equation 49 and let's measure it this numerically when we do this relaxation time, time-dependent relaxation time against the total QCD kinetics. You observe that this figure presents, again, differences. And the main issue is that the relaxation scale, being just one unique scale of all the modes that you have in your theory, slows down faster towards its equilibrated value defined by the Navier-Stokes, which in this case, this ratio is 1. While QCD kinetics, it has diffusion of momenta, and therefore it slows down because you have to populate via cascading from different sectors of momenta towards higher sectors of momenta. And therefore the thermalization process is slowed down by that. But even with that, we observe that at very early times, they share similar properties, of course, although we cannot do that, we could not really go until very W equals 0 because of numerics, but we see that there is a trend of the black and the blue figure to overlap, and the difference are in the middle, but at late times, again, you see that both of them converge towards the fixed point, which is an indication of a late time and an early time attractor. So now, I said before that we have a behavior where you have an early time and an early time attractor. And right now, with in our latest paper, we show Ali and Hao Chen, we realize that when you have this type of behavior, it's really people is
ask a naive question. So does, in order to make this comparison, so now presumably you tuned the relaxation time so that it fits the QCD kinetics. Is that right?
At late time.
So that was precisely my question, because in some ways they agree at early times, and then at late times, I mean, like if you had tuned them asymptotically at late times, wouldn't you think that the two curves are on top of one another at late times?
But you tune it with...
Actually, okay, just the one is already the tuning. Okay, I see. So the fact that they land on the same one, that's the fact that you've tuned them. And so the fact that they disagree is loosely speaking that the second order transport coefficients are not the same even after you tuned the first order one. Is
yes,
that right?
correct.
Okay, very good.
But regardless of that, even when you do this type of comparison, which I feel that is a one-to-one, you see that the difference is 10%.
Yeah, that's indeed kind of remarkable, because in principle, you know, there's all this bottom-up thermalization, which is supposedly really unusual and so on. And in the end, it doesn't make that much of a difference.
Exactly. And part of the reason is that, and that's what I was trying to say, like in the last paper with Ali, Shou, and Hao Chen, we went through a complete, very obscure mathematical technique, but what you understand at the very end of the exercise that we did is that those type of universal curves that everybody's talking about, they call attractor solution. We are very against that particular name because in general, attractors are not solutions of anything. So what happens is that at late times, the fact that both models have a gradient expansion means that they share the same forward attractor, because at late times all the solutions merge. And also, when you are looking at what happens at early times, you see that there are no minor differences, and it's because again the free streaming dominates in that particular regime, no matter what type of microscopic theory you have. And that is related with the fact that when you write in terms of this on the strength of the gradient, which is this variable W, it is just telling you that you have also a pullback attractor. And that is kind of the new point that we are trying to make when you try to understand this figure, is because you have a pullback attractor and a forward attractor, and the differences are in the middle, which is precisely what correctly encodes figure 2. But that doesn't matter, because at the end, the trend is more or less the same. And we see that even if you have all this complicated theory, the difference is only 10%. So that is kind of good news up to some extent. And now it's the second part of the paper, which starts in section 4. And since I may run out of time, I will try to speed up. And here we use the same strategy. So what we do is to derive an equation for the linear perturbation around the background. And therefore, you have not only spatial, now you have to take into account spatial inhomogeneities that break down the symmetry of the background, in this case, the Bjorken. So that's why you have now spatial gradients there and longitudinal ones. These derivatives in respect to I in the right-hand side and respect to sigma. But you have to also perturbate all the possible variables that you have. And in this case, is also the possible time dependence of your relaxation scale, the perturbations that go into the distribution function. That's why you have perturbations of the fluid velocity, and so on. And we reduce this is the most generic equation that you can have, at least within our approach, but we really want to, since you start to put out a lot of equations and you don't get any physics. So we break under certain control the symmetry, and we are just going to assume that we break the symmetry only in the transverse plane. So now we will have a little bit of dynamics in the transverse plane, and that's what is encoded in equation 57 after you do a Fourier transform. So now, instead of having an X dependence, I'm going to analyze what happens in the wave number K. And this has a very, very practical purpose, which is that you can write equation 61 for that particular case. This is the equation of the perturbations when you just break slowly, as I like to call it, or under control the symmetry in the transverse plane. And again, you use the same strategy. And here is why we use the harmonic spherics, because now you break the symmetry and we expand basically in terms of harmonic spherics moments, which is nothing else than moments of this delta F. So we use the same strategy. What is the advantage? Again, you can write all the possible components of the energy momentum tensor under this perturbation equation 63, which are all those terms, and this is just taking into account different momentum fluxes, different the shear components, the IJ components, and so on. And it's really useful because, again, instead of solving this complicated and horrible equation 61, you solve a kind of also horrible, complicated equation of those moments, but it's more under control because you can add more moments, and then you know that you are going to converge towards the solution after adding. In this case, since there are many of those moments, we went until like 48 or 32, I don't recall right now, in order to see that there is a convergence. But indeed, it does converge. So that's the cool thing, which is precisely encoded in equation 64. And let's avoid those details. This is nothing else than an equation of the moments. And notice that now you have mixtures not only with the index L, which happened before, but also the index M. So notice that in the background, because I have my symmetry is protected because of the there was no transverse dynamics. Now it's not, and that's why now I have mixtures not only in the index L, but also in the index M, and that's what makes the equations a little bit more cumbersome. By the way, even though we didn't publish this, it's in some notes that someday will come out to the light. Those equations also have certain resurgent properties that I think that still deserve more understanding, because it captures information about how the spatial inhomogeneities decay asymptotically or even at early time. How does it behave? So we did not explore this in this work because our purpose was to illustrate the method and show the generalities when you compare with QCD kinetics. Okay, so let me just go to the plots because I am almost running out of time. And just before of that, so we have perturbations. In order to, again, solve this numerically, you need initial conditions. And the simplest case that we did was to perform a perturbation of the distribution function by using this initial condition in CGC, and this was done by in the paper of Derectini, the compost original paper. So we took the same structure, and this is the equation 80 is our initial condition for the momentum perturbations, and this equation 74 is the perturbations at the level of the energy density, of the delta F, and from that we can initialize the system. Now, as I said, my goal is to calculate the green function, and then you need some equation or some way to connect. And the way that we know in physics is that it's in equation 91, which is what I call the master equation. And Thomas and I, and maybe some Mitchell and others recognize this equation, which is nothing else that if you perturbate the system at a tau, how to propagate the information of your initial perturbation, which is in your right-hand side from the initial energy momentum tensor at tau 0, is encoded in the green function. And therefore, you can really easily recognize that if you start to write how these different components of the energy moment of the green function are related with the components of your perturbed energy momentum tensor, you can really find out relations among them, which is in terms of those moments, which is encoded. Let me see the equations. Okay, we didn't put it, but either way, all what I'm saying is that since the green function is in terms of the components of your perturbed energy momentum tensor, and the perturbed energy momentum tensor is a function of those moments, you can really reconstruct all the components of your green function. Is that understood?
Let me see. That's simply because we linearized everything in the perturbation. So this differential equation as a differential equation in the delta F is just purely linear.
Correct.
Formally, I can always just read off the green function.
Yes.
Okay.
So, okay, and with this being said, let me just jump into the plots that are in figure 3 and 4, and I encourage you here to, if you focus in at least in the perturbations, the energy response, Thomas, in the left-hand side at the top, and please do assume like until 700, because unfortunately the choice of colors was not necessarily the best. Can you zoom, please? In page 12 at the top.
Let me see. So this is page 12. You want just the left figure?
Either, yes, the left, but you can zoom because it's just that the colors didn't help for something that I'm going to say there. So I remember that I have to do the zoom like big to differentiate the black color.
Can you see it? What you want to see?
Yes, yes, I see it. So here I just have solutions of the reconstruction of this green function. In this case, it's nothing else that you can imagine that the temporal components of your green function. And in general, when you study hydrodynamics and you do the same exercise, this is the propagation of a sound wave. Now, the numerics that we already, and I didn't say that, and then what we have here that is what you have in the vertical axis. In the longitudinal axis, you have the wave number times the step in time, this k delta tau, because it's more convenient to study like that, because that is the propagation of the spatial inhomogeneities when you break the symmetry at the level of the background. And what we have is a different colors. The colors are the different values of W. And as I said, the cool thing about this value W is that you are really measuring the strength. So what we are seeing is systematically with the change of color, how much is changed the propagation of the perturbation for a given gradient. And you see, you observe that the shorter the blue, the bluer the color of the figure, the closer you are to the free streaming case, which is the black line that if you zoom very, very, very close, you will see the black line. That is a very bad choice of color because you see that black and blue do not differentiate much. While when the system is above around 1, which is more or less when hydrodynamic works, starts to work in the gradient expansion, then you start to see that this is the propagation of the sound wave. So what you see basically there is the decay of many modes that are encoded there towards the hydrodynamical behavior. And the larger the W, then the closer you are to hydrodynamics. And that is precisely the information that is encoded in this plot, which you see that this is just the propagation of all those modes compared with the hydrodynamical ones. So this is the cool thing of this plot that I like it a lot, because you see how much is the difference when you have like very, very far from equilibrium, and at the same time when you are more close to hydrodynamics. And the other thing that is interesting is that if the system is almost going at in free streaming, they are basically no interactions, so they are moving almost at the speed of light, and therefore they are just like getting away, while the modes that are more like hydrodynamics, they evolve more slowly. And that is precisely why you see that the amplitude is much more larger when the W is larger. So that is kind of what I wanted to emphasize there. Now, if you go to, and similar plots were done in figure 4, let's avoid the discussion there. And for the figure 4, actually, the only important part is that we also compare the shear stress response, which are more like momentum fluxes. And you see that actually the amplitude that behaves a little bit different, because particles are escaping away, so the amplitude has to be larger. So let's not, let me just go to figure 5, which is more interesting in my opinion. And figure 5, we compare again the green function by using our method with what is derived from QCD, and also free streaming. So the solid lines are the solutions obtained from the green function, the relaxation time approximation, and the dotted lines are what you obtain for kinetics in QCD. And you see that there are similar features. The main differences that we observe are the broadening in the peaks, where those functions are really like kind of broadening. And as I said, this is related with, in kinetics, in kinetics QCD, there is diffusion of momentum at different rates for different modes. So therefore, the system thermalizes or hydrodynamizes later. And that is precisely why you see that in general, in each of those plots, the peaks of the distributions as a given values of W are larger compared with the perturbations that you have in the relaxation time approximation. So keep in mind that when I say the perturbations, here there is no constant relaxation time, because the relaxation time depends on time, and therefore you have to also consider perturbations of the temperature. So there is a little bit of diffusion of momentum, but it's not really not enough or comparable with perturbative QCD. However, when we really quantify what are the differences between all those type of models, we obtain again that there are no difference more larger than 10%. So even at the level of the green function, what we observe at the level of the background and also the linearized green function, we observe that the differences are really not so large. And therefore, up to some extent with great confidence, if you use relaxation time, it can give you many of the features that you expect from kinetics QCD, which is more complicated, more complete microscopically, but maybe it's not. You don't gain too much at linear when you do a linear perturbation if you do use any of those theories. Also, notice that the late time behavior is equivalent for all the perturbations that you have, and it's again an indication that there is a late time attractor behavior for those perturbations too, which is somehow expected because you expect that all the propagation diffuse, and at the end you just go towards its fixed point at infinity. So that is kind of the bottom line of this plot. Also something similar in figure 6. And well, I think that was the purpose of this paper, was mostly to illustrate that you want to quantify what are the differences when you do a one-to-one comparison in different microscopic models for different different propagation of different modes on top of a non-equilibrium background, and there are differences, but the difference in general, as we state in the at the end of the section 5 in page 16, they are 10%, and this is 10% is actually happening when this variable W that determines the beginning of hydrodynamics when they become applicable. So when hydro become applicable is when we observe the largest difference, but there are certain universal behavior, no matter in which, either if you are in early time or late time behavior. And also, it is interesting to quantify, because right now, at least there is information of experiments, especially with photons in quark matter. There was a very interesting ongoing work where they really start to show that there is an increase of 30% in photon production in certain kinematic PT region if you include pre-equilibrium physics. So this means that all what we knew about pre-equilibrium production of particles might become again relevant. I did some work about that in my PhD. And we knew that, but at that time, it was there was less information from experimental data. And now all those works are also pointing out that there are some lessons that we can learn also about particle multiplicity. There was a very cool work of Soren about, and it was a subject in a seminar like 2 weeks ago in Seattle about entropy production during the pre-equilibrium phase. And that was precisely one of the main aspects that was discussed in that work, that there is some interesting information that you can constrain the entropy and therefore the particle multiplicity of that you produce in those collisions by analyzing which will help us to constrain how much of dynamics we have in the pre-equilibrium phase. So I think that all those ideas that some of us studied back in the day are coming back, but now more precise and concise. And I think that all this work of attractors and hydrodynamization is helping us to sharpen much better and much more quantitative different aspects. In this case, in this work was like, okay, if I use two different microscopic models, what is the gain? And the answer is, well, at least in those two models, we see a 10% difference that can be translated into uncertainties in particle production, and therefore I can constrain better the microscopic picture by analyzing observables. Photons is one candidate. I have other one, which is the leptons, and so on. So, okay, this is what I wanted to tell you. This is what this work was about. And there are ways to extend also this. We did not analyze this kind of late time behavior, this attractor that you see at the level of the perturbations. And of course, this is something that hopefully will be done.
Can I ask you something?
Yeah.
So you mentioned in response to Thomas that there was you see a pullback attractor, right? What I see in that picture is really not a pullback attractor. A pullback attractor is one when you fix tau and send tau 0 to 0. Then you see a bounded solution.
But as I say, we are these figures. You are thinking in terms of. I am talking in terms of this variable W.
Okay, so this is a different. Okay.
Yes,
so
we are not analyzing. Yes, we are not analyzing. In the you are right that, and that is something that also came up with in our work. Thanks for mentioning this. That thanks for mentioning this. This is important aspect. Thank you, Manny. So that is something that I did not explain because it's too long a story. But I changed the variable, and I changed originally your dynamics. The original dynamics of the problem, really, of your original problem, is in the proper time, tau. And something that we realized with Ali in our first paper was that if you study other systems and you try to do that in this variable W, we were not observing this line that people were talking about. And what we understood is that you change the variable from tau to this W or this X in figure 1. Let's focus in figure 2, sorry. And then what you do is a dimensionally reduction of the equations of motion, but you pay a price, which is that the original singularity that you have in tau, you map to somewhere else in the value of the shear. And it's only in that case that you see that when you take the limit W going to W0 equals 0, then all the kind of, there is like a unique line emerging in that variable. But if you do that in the original dynamical theory, which is in the proper time tau, this unique line never exists because you have a singularity there. And that is part of the kind of confusion between many people. And we have really stressed this continuously. And finally, some of them are catching up with what we express because they were talking about this universality, and its universality if you change the variable and you dimensionally reduce. If not, then you will never see this type of line if you originally plot this in real time.
So in other words, this tau to T times tau or temperature times tau is not a homeomorphism, or in some sense it changes the topology of the original phase space. And that's why it is not a valid transformation in the early times, but people keep saying that, oh, I mean, we find this, line W equals 0, around W equals 0, because, you change the topology of the problem and it's not the same problem anymore. That's why, we do see such a convergence. But if you go to tau, because original equations are singular exactly at that point, tau 0, then you cannot, really claim that this is the same problem. It's just like you're changing it to a, in some sense, a toy model, I call it, right?
But I mean, in this plot, in any event, you're not varying initial conditions. You're just comparing two different evolutions of the same initial condition.
So that was another question that I was asking, when you call pullback attractor, you have to really fix tau and send tau 0 to 0. If you see a bounded solution, that's called pullback attractor. That's a real attractor. But yeah, Thomas is right in the sense that you're really looking at the, in some sense, past forward attractor and future forward attractor by changing tau and fixing tau 0.
I mean, the numeric was done by, and we also did the same. Remember that we put tau 0 as close to 0, and then we just map this information in terms of W, just to see that. That's what you do numerically.
Yeah, but it is true that the system might have a pullback attractor in W coordinates.
Yes, in W, yes.
In
W, yes, definitely, but not in tau. I agree with you.
Another question is, what did you really learn by studying resurgence? You mentioned it, but really you see this from the get-go. You're talking about the linearized equations. I mean, I just don't get the idea of, talking about resurgence, because, you cannot really push away from the fixed points if you're studying.
What do you mean?
So imagine that you have a linearized equation, right? I'm assuming that you're linearizing everything because your perturbations
it's linear. We are not doing anything beyond than linear. That's true. Yeah.
So you're really talking about resurgence. I think did you solve something using resurgence?
No, we didn't. I mean, those are just notes that we already have, but we have not really done much. The point is that at the level of the perturbations, you not only are coupling with perturbations, you couple with the background. And remember that we solved this problem together, that the background has the equations for the background moments. They have resurgent properties, as you know.
By resurgence properties, you mean like they have like some exponential type?
Yes,
behavior? Is that
exactly.
What you mean?
And here yes, that's what I meant. Like,
yeah, but resurgence really means that if you can connect that information to the information of early times, and so a lot of times people say this, but really you have to solve the original equation, nonlinear equation, not the linearized one, because linearized one is only valid around the fixed point.
Right. But we are solving. So in other words, the idea, we have not published this, that's why we did not include it, because we didn't go further. But you can show, and you and I did this, that for the background, you can do this connection between the UV and the IR.
be a
Yes,
result.
because your perturbations are not crazy enough. I mean,
Exactly.
they work enough, so they might actually introduce something, you know, some other fixed points. Then it is really
Exactly.
hard
We
to
have
talk
not
about.
done the analysis here. We just analyze what happens when you are close to the fixed points in the IR, in this case for the perturbations. And we see that there is some information coming from the couplings with the background times the decay of the inhomogeneities, especially inhomogeneities, which are weighted by this, the product of the wave number times the proper time. And what I meant is that all the Lyapunov exponents have this particular behavior, and we can systematically start to expand. But it's true that we did not analyze yet what happens in the UV. So that's why I'm just saying, like, there is certain features there that needs to be better understood.
Can I just ask a kind of technical question? So this green function, so the equations are totally linear, but the coefficients, of course, are time dependent. So it's still a kind of time ordered exponential or something, is it, of, you know, some big matrix? So
it's a big matrix, yes.
Yeah. So do you just numerically integrate the equations to get the green function, or do you somehow formally take this matrix exponential?
No, we reconstruct the green function. So if you see
by numerically solving the differential equations.
Yes.
Oh, okay.
And then we just, since we can do a one-to-one map between the green function and the perturbations of the energy momentum tensor.
Since everything's linear, so
Exactly.
It doesn't matter. You just pick any initial condition, you propagate it forward, and then you read off the green function. You don't try to construct some kind of complicated matrix exponential or something.
No,
okay.
no. But it works because of the perturbations also have couplings with the background, so there is a lot of nonlinearity there.
Yeah.
So it's much more nonlinear than what we naively think. Something that we want to even test numerically, and it's possible to do that within this setup, is like how good is this linear response on top of a background, which is an assumption, really. Nobody has tested even in compost, which is what people is using, against, for instance, a real 3+1 solver in relaxation time approximation. That would be really nice to do that, because you can really validate all these assumptions that has been made by hand, and even what you and I have been doing in hydrokinetics is the same. And something that is possible to study within this approach is how good is this linear response on top of of a more full nonlinear system that is expanding not only longitudinally but also in the transverse dimension. Okay. That is something that can be extended, this study, in order to provide a more solid evidence that linear response can work even in those cases. I don't have an answer. I think that nobody has, and right now it's an assumption, literally.
Maurizio, can I ask you something?
Sure.
So in the pure Bjorken model, like you see another fixed point, right, in early times.
Yeah.
Do you have that here too, or you
No, we just pick up when the longitudinal pressure is 0.
Oh, so it is fine-tuned to only go there.
Yes, and the reason is because we were having in mind, and you can see that exactly. That's why I said, and Thomas also asked me about that. Let me just put equation 29, which is an equation that people uses in phenomenological studies within the color glass condensate approach. So usually the arguments are that if you do QCD, real QCD, that's the result. And we were just having in mind, and that is equivalent to what we call prolate.
I see. So you already fixed this too. That's what also Thomas asked that I now remember. That if you change this delta, you know, if you put PT there, then it becomes the other fixed point. But so to some extent, you don't care about that fixed point. You just care about this other one.
Yes. Yeah. And we did it because that's why we quote in the, if you read a little bit above of equation 29, it's something related with previous works in color glass condensate. And I mean, as I said, I didn't mind about the initial condition, really, if you ask me my opinion.
Yeah.
But it was more for the illustration of how it works.
But the point is that if that changes, that initial condition changes, then you probably go to a different fixed point, so you wouldn't have those, you know.
I mean, for the background, I don't think that you go somewhere else, because we know that, and we studied this together.
Yeah, but if you change, for instance, P var sigma to PT in your 29 inside delta function, then you would go to that fixed point, right? Because you're now.
Yes, you can do that. Yes, you can do that, but I think that it does not affect the late time.
Right, right. No, I mean, because in late time you only have one.
Yeah. No, I agree. I agree.
Yes. No, early time. I meant early times. Yeah.
Yeah. And I think that the matching of this constant that it was done here also is not going to affect this tau to the 4/3 times the energy at infinity. I don't think. I mean, that changes the number, but once you do that in the way that we do, it's not going to matter, because at late times we know that everything hydrodynamizes and gradient expansion works. At least for Bjorken, we know that it's not general for generic flows, and that's what we studied in the Gutser.
Yeah, I mean, I think the part you say that down here, the part that I also kind of confused me is that indeed there is a sort of miracle about relaxation time. You would think that this ansatz still has a lot of degrees of freedom, because, you know, this initial spectrum in transverse momentum could look arbitrarily complicated. But you say that for relaxation time, it actually makes no difference at all what it looks like.
Yeah, that's what it looks like. I think that is because we basically, and that was also surprising for us. I mean, I was the first one who was like, how could it be? But the more we were revisiting, the more we were like, that's what it is. And it's true, when you, even if you have this simple relaxation time, you also have all those modes, but all those modes decay at the same rate, while the real QCD theory has like more diffusion of momenta from some sector to another in momentum, and therefore it will be very slow, and it's slower. But how much and how fast it affects the observables that you really care about, in this case energy momentum tensor, is not large. My point to take is that it's going to affect actually, and that's something that we didn't do, but at least Ali and I have some evidence on that, that it affects much more when you start to analyze other moments related with momentum tails. That's where you will see differences. But since energy momentum tensor is actually the softest modes of the system, you can really say like, well, it doesn't matter. But I at least Ali and I know that when you start to look to moments that really weight tails of the energy tails, then you will see differences. And actually it makes sense, because over there the diffusion of momenta matters in order to the system to populate and to get to the thermal values.
Well, this was mentioned in our paper with.
Yes, exactly. We mentioned. That's why I'm saying like it has not been done I know it was recent. It was done like last week in a paper of Mike Strickland. They actually point out that when you use QCD kinetics, it actually affects much more than what we think. And we knew that also because we observed the same in our paper with Hao Cheng and Cho and Ali. But the energy momentum tensor does not have larger sensitivity.
Okie dokie. Yes, I have another call in about 10 minutes or so. But that was great. That was really useful.
Thank you. Thank you so much.
And I actually have recorded it, so I don't know, I can send you a link at some point.
Perfect. Thank you so much for the invitation and for being here, everybody, for the conversations.
Okay. Well, everybody stay well.
Yep. Thanks. Bye.